Every single day, we're all doing stuff online, sending emails, buying things, sharing personal info, and we really don't give it a second thought. But have you ever stopped and wondered what invisible shield is actually protecting all that data as it zips across the internet? Well, that shield is modern encryption, and today we're going to pull back the curtain and see how it really works. I mean, it's a huge question, isn't it? Because without some kind of powerful security system, every single message, every password, every credit card number we send would basically be an open book for anyone and everyone to read. Well, the answer isn't some single magic bullet. It's more like a whole toolkit of cryptographic techniques. Today, we're going to look at two of the most important tools in that kit: a super powerful digital lock for scrambling your data, and a unique digital fingerprint for making sure it's authentic. All right, let's open up that toolkit. Our first tool is the real workhorse of modern encryption. It's a type of digital lock called a block cipher, and the undisputed champion in this category is something called AES. So AES, that stands for Advanced Encryption Standard. And trust me, it's the global gold standard for the stuff. It actually won a worldwide competition to find the best, most secure encryption method. The way it works is by taking a tiny, fixed-sized chunk of your data, just 128 bits, and scrambling it using a secret key. But it's not just a one-and-done mix. It happens over and over again through multiple, really complex rounds, which makes the data completely unreadable to anyone without the key. So just take a look at this. On the left, you've got your normal readable data. We call that plain text. It goes into the encryption engine, where it gets all mixed up with a secret key and gets put through this whole series of complicated transformations, what the pros call rounds. After all that, what pops out on the other side is ciphertext, a totally scrambled, unreadable version of your original data. And the only way to reverse this process is if you have the exact right key. Okay, so AES is amazing at encrypting one tiny 128-bit block of data. But wait a minute, that kind of brings up a pretty obvious problem, right? I mean, think about it. An email, a photo, a movie, these things are huge, way, way bigger than 128 bits. We can't just encrypt the very first little piece and call it a day. So how do we solve this massive size problem? So the trick is, we need a strategy. We need a recipe for how to use our digital lock over and over and over again on a long message. In the world of cryptography, these recipes are called modes of operation, and they are absolutely crucial for turning a simple block cipher into a tool that can encrypt pretty much anything, no matter the size. But here's the thing. Not all these recipes are cooked up the same. To really get why, let's look at a tale of two different methods. You'll see how a small change in the strategy can have a huge impact on your security. Okay, so the simplest, most straightforward way is something called electronic codebook, or ECB. The idea is dead simple. You chop your message up into little 128-bit blocks, and then you encrypt each one all by itself using the exact same secret key. Easy, right? It's simple, it's fast. But that simplicity is hiding a really dangerous flaw. And here it is. This is the killer flaw. Because ECB treats every identical block the exact same way, any patterns in your original data are perfectly preserved in the encrypted result. So an identical block of plain text will always produce the same block of ciphertext. If you encrypt an image, you can still see the outline of the original, even though it's technically encrypted. And that is a massive security vulnerability. So if encrypting blocks independently is so bad, what's the fix? Well, the answer is actually pretty elegant. You create a chain. And this is how you do it. This is a much, much better way called cipher block chaining, or CBC. Here, before a block of plain text gets encrypted, it's first mixed with the encrypted result of the block that came right before it. That one little step, that chaining, it completely obliterates the patterns. So now, even if you have two identical plain text blocks, they will result in completely different ciphertext blocks. The output just looks like random noise, which is exactly what you want for strong encryption. All right, so we've got our digital lock, AES, to keep our data secret. Awesome. But, secrecy is really only half the battle. How do we know that the data we just received is the actual data that was sent? How can we trust that it hasn't been messed with? For that, we need a whole different tool from our kit. This tool is called a cryptographic hash function. Just think of it like this amazing data blender. You can feed it anything, a single word, a whole book, an entire movie, and it will always spit out a short, fixed-length string of characters. That unique output, that's called a hash. Honestly, the best way to think about it is like a unique digital fingerprint for your data. You feed in the word fox, you get a specific fingerprint. You feed in a whole sentence, you get a totally different one. But here's the real magic. If you change just one single letter in that sentence, bam, the fingerprint changes completely. It's totally unrecognizable. This extreme sensitivity to change is what makes it so powerful. Now, for one of these fingerprints to be actually secure, it's got to have three really important properties. First, it has to be a one-way street. You can't just look at the fingerprint and figure out what the original data was. Second, it's got to be deterministic. The same file will create the exact same hash every single time. And finally, it has to be collision resistant, which is a fancy way of saying it's practically impossible for two different files to ever have the same fingerprint. So we've got this incredible digital fingerprinting tool, but where does it actually show up in the real world? The answer is pretty much everywhere. Let's look at just a few examples of how hashing builds the trust we rely on every single day. So, one of the biggest uses is in what we call digital signatures. Alice doesn't sign her whole long message. Instead, she just creates a short hash of it, its fingerprint. Then she encrypts that little fingerprint with her unique private key, a key that only she has. That's the digital signature. When Bob gets it, he can use Alice's public key, which is available to everyone, to unlock the fingerprint. If it unlocks properly and matches the hash he calculates himself, he knows two things for sure. The message is really from Alice, and it hasn't been changed one bit. Oh, this is a huge one, and it affects all of us. No responsible website should ever store your password directly. Instead, they store a hash of your password. That way, if their database ever gets stolen, the bad guys don't get your actual password. They just get a list of hashes, which, like we said, are one way and can't be reversed. It's a fundamental layer of your security. And finally, have you ever downloaded a big file and next to the download link, you see this super long string of random letters and numbers? That's a hash. It's the file's fingerprint, or its message digest. You can run that file you downloaded through the same hashing tool on your own computer. And if the fingerprint you get matches the one on the website, you can be 100% sure that your file is an exact, uncorrupted copy of the original. So there you have it. From scrambling our data with digital locks like AES to verifying it with digital fingerprints from hashing. These are the fundamental tools that build the trust and privacy we all kind of take for granted online. But the world of security is a constant arms race, which leaves us with a final question to think about. As our computers get more and more powerful and the threats get more sophisticated, what's the next generation of our digital security toolkit going to look like?